All right. So here we have a graph of function force versus position, right? And then it says estimate the work done by the force represented by the graph that you see here, figure 7-30, in displacing a particle from x equals 1 to x equals 3. Okay, so we want to go from here to here. Okay, so refine your method, right, to see how close you can come to the exact answer of 6 joules. Okay, so they already gave you the answer, so they want to see if you could get to it. The curve is given by analytically by force is equal to a over x squared, where a happens to be 9 newtons meters squared. Show how to calculate the work done by rules of integration. I will worry about that later. But for now, what I'm going to do is I'm going to break these up into small sections to get the area. So here, I'm going to call this area area 1, okay? And then here, I'm going to consider this to be my area 2, okay? And then this will be area 3, and then area 4. Thank God there's no area 52. All right. So if we could sort of estimate these areas, okay, and add them all up, and that will pretty much become the work done between 1 to 3 meters, right? So we could simply say the work done by F over delta X of 1 to 3 meters is simply just the area 1, I guess, plus area 2, right, plus area 3, right, plus area 4, right? So to calculate the area 1 seems like I'm going to split this up into 2 parts right here. So here, this looks like 4, and right here is 0.5 because this is 1, and half of that is 0.5. So here, 0.5, and here's 4. So I have 4 times 0.5, right? Plus, I have this little triangle part right here. Looks like it's going all the way up to 9, and then it's coming down to 4. So half of 0.5 times 5, right? So 5, because here's 1, 2, 3, 4, 5. 5 times 1 half times 1 half, right? So we're going to have to add these two to get the total area 1. What about area 2? Area 2 looks like I could split this up into 2 parts and say, this looks like 2, right? So 2 times, right, 0.5 again, right, which is a base, plus here looks like 2, but 1 half of 2 times 0.5 again, right? Because that looks like 2, and it's a triangle, right? Almost a triangle. And then for area 3, it looks like I have 1 times 0.5, right? And then I got this little triangle up here, which is like 1 half of, right, 1 times 0.5. And here it looks like it's just 1 times 0.5, because for area 4 it's just 1 times 0.5, because I'm going to have that little extra here, but we're going to add that to some other place. And so 1 times 0.5. So let's work it out. So here I have 2 plus half of 5 is 2.5, and half of 2.5 is 1.25, right? And then here plus this will be 1, right? Plus 0.5, because half of 2 is 1, and 1 times 0.5 is 0.5. Plus here I have 0.5 plus half of 1 is half times 0.5, right? So 0.5 times 0.5 is 0.25. Here I have plus 0.5. So let's add them all up, right? So this is 3.25 plus 1.5 plus 0.75 plus 0.5. So this here is 4, 5.5, well, 6. I'm just so awesome, right? Oh, that's just, right? What an estimate. What an estimate. All right. Now they want us to calculate using the real function, right? So since they say work is equal to the integral of x1 to x2 of function f of x dx, right? Now, f of x is obviously the force function, right? So this is the general equation here. But since we have, right, this f of x as 9 over x squared, and our x initial, or x1, is 1, 2, 3. Okay? Dx. So if I want to rewrite this, right, I could simply say 1 to 3, 9 times x to the negative second power dx is what you can write down. And since integration is like antiderivative, so antiderivative will be adding a power, right? So you get 9x to the negative 1, because if we add a power, it becomes negative 1. Divide that by negative 1. Evaluate it from 1 to 3. So let's rewrite this, right, without the negative power here. So this negative 1 can be negative 9 over x at the bottom. Okay? And then, if we evaluate that from 1 to 3, let's see what we get. So, let's evaluate that with 3 first. So, negative 9 over 3 minus negative 9 over 1. What's negative 9 over 3? That's negative 3 minus negative 9. So, negative 3 minus negative 9 is positive 9, minus 3 is positive 6 joules. Same thing. Okay? Alrighty. Any questions so far? All right. All right. Let's take a look at the next problem here. So Here it says figure 7-32 shows a spring with a pointer attached hanging next to a scale graduated in millimeters. Now, yes, scale graduated in millimeters can be interpreted as a fancy way of saying we have a ruler next to it. That's all it means, really, right? It's a friggin' ruler. So the three different weights are hung from a spring, in turn, as shown, right? So what's happening is we actually have this weight that's hanging here, right? And then it's basically saying, okay, if I put 110 Newton weight on this spring, it stretches to 40 millimeters. And then when I hang a different weight, like 240 Newtons of weight, onto the same spring, now it is stretched to 60 millimeters. That does not mean that when I take these weights off, the spring's going to go back to zero. We cannot assume that, right? It's going to spring back to a certain point around here somewhere, and I have no idea where it's going to be hanging to. So we cannot assume that when we take this weight off, the spring's going to go back, contract to zero. We cannot assume that. So maybe it's a good idea to figure out what the K value of this spring is. Right? Now, since we know generally, right, force of spring is equal to Kx. Okay? So I'm going to leave the negative out because I just want to basically work with the magnitude because we know, force of spring is a restorative force. So if you compress the spring in the negative direction, the force is going to want to come out to the positive direction. And if you stretch out in the positive direction, the force wants to go into the negative direction to come back. So that negative is just showing the direction. So I want to basically leave the negative out and just graph this, John, so that we can actually see how this thing is going to behave if we were to graph it out. So here's what I'm going to do. I'm going to graph, here's my position X, and I'm going to put this in meters, okay? And here is my force of spring. And this force of spring is measured in newtons, but this force applied to the spring is really nothing more than just the weight of this thing, mg, right? Because whatever weight that I'm hanging on this thing is how much force that I'm applying to the spring, and the spring is going to basically work in the opposite direction, all right? So if I were to take a look at what's going on with this first one, when I apply 110 newtons of force onto this spring, basically it moved out to, right, 0.040 meters. So here, is where the first spring, well, these are all same springs, but the first scenario of that spring. Then, when I apply 240 newtons onto that spring, right, it basically stretched out to 0.6, or 0.06, I should say, right? So 0.06, I'm going to try to do my best to So 0.06 meters is where it's indicated. So if I were to do this, the slope value between these 2 points would represent my K, right? So this K right here is the slope value. Does that make sense? Right? So here is my rise, right? And which is basically delta F, right? And here's my run, which is delta X. So we can simply say, right, the slope value which is equal to rise over run, right? So if we work it out, okay, delta F is 240 minus 110. Delta X is 0.06 minus 0.04. So if you work it out, I think you'll get something like 6,500 newtons per meter. So that's my spring constant K. Deal? So if I were to remove all this weight, where would it go back to? It's not going to be zero, I guarantee that. So let's just take a look at the 110 Newton one right here, right? We know F spring is equal to, right, Kx. How much did it stretch? Well, we know if I were to place 110 newtons of force with a spring constant of 6,500, I want to know how much it stretched. If I solve for x, my x is then 110 over 6,500. So if I do this, it comes out to be 0.0169 meters, or around, right, 0.017 meters. That means when I placed 110 newtons, it only stretched 17 millimeters. So if I take this thing off, it's going to go up 17 millimeters. So the spring will actually return to, right? It will return to 23 millimeter point. Because this distance here that it stretched happens to be 17 millimeters. Does that make sense? Okay. If you want to use this one, you could have done the same, right? If you wanted to use this 240, right, you could have done the same. So what happens if you use 240 divide by 6,500 for my purple X? So for my purple X, it is equal to 240 divided by 6,500. And you'll get, what do you get? You get 0.0369, right? So if you were to subtract 60, right, from that, so you could simply say it's like 0.037 meters, right? And if you subtract 60 from that, guess what? You get exactly 23 again, right? So it starts at, right? So it starts at 23 millimeters at equilibrium point, okay? So you can say your X naught is equal to 23 millimeters. Is that good? All right. So here, I guess EQPT is equal to 40 minus 17. Right? And then for this one, I guess EQPT is equal to 60 minus 37. Right? And they both come out to be 23. All right, then. Now that we know that, when I put a mystery mass on, right, here, F spring, which is equal to basically the mystery mass W, right, which is basically Fg, right, and that is equal to Kx, right? But what is this X? This X now here is equal to, right, 30 minus 27. So since this is, 23, right? So this X is equal to 30 minus 23. So my X, the amount of stretch, happens to be 7 millimeters. So my X is 7 millimeters, or 007 meters. So that's what we're going to actually put in for my X. We already know what K is. So we can find what this weight is, because now we can say, since 6,500 newtons per meter times 007 meters it should come out to 45.5 newtons. Okay? Any questions? Alrighty then. Let's take a look at the next one here. All right, this gets kind of involved. So here we have a 3 kilogram block that is attached to the lower end of a vertical spring, right, is oscillating up and down with an amplitude of 0.05 meters. So when it's oscillating 0.05 meters, from the midpoint of this system, which is actually equilibrium position of my whole block spring system, right? So this here is, I guess, block spring system. Equilibrium, right? So this position right here is block spring system's equilibrium. So when I place this 3 kilogram block on it, it's going to go stretch down to this position. We don't know exactly, right, how much this thing's going to stretch. We can find out though, right? So if we were to think about, F spring is equal to Kx, how much would 3 kilogram stretch this thing out to? Let's find out. So here I say 3 kilograms times 9.8 is equal to, the K value is 90 newtons per meter. So we can use that, right? So 90 newtons per meter times X. Now this X here is how much this thing is going to stretch from here to here is what I'm looking for as this X. Okay? So let's find out. How much does it stretch? So if I'm looking for this, so what's this? This is 3 times 9.8, and I get 29.4 is equal to 90x. So my x is equal to, so divide that by 90, and I get 0.327, right, meters. So this thing will stretch 0.27 meters. Okay? So I'm going to say here is 0.327 meters. Now, when this thing goes up 0.05 meters, this location here is basically 0.327 minus 0.05. So this location here happens to be 0.277 meters. Are we okay with that? All right. So hopefully now we know what's going on. Okay. So when this thing actually travels all the way down, okay, it goes to 0.327 meters from unstretched spring. When I put the 3 kilogram mass on it, it's going to stretch down to 0.327 meters. Then it's going to oscillate up 0.05 and then down to 3.27 and then below that 0.05. So it's going to oscillate back and forth, back and forth. Okay. You could say that here at this location is like in a point, this is 0.377 meters, right? This point right here. All right. So now let's take a look at what's going on with part A. Part A asks how much work is done on the block by the weight force. So they want to know what work done by gravity is, right? Work done by gravity. Work done by gravity, right, is equal to Fg dot delta y, right? So when it goes from the highest point to the midpoint, so my delta y is only traveling this much, 0.05 meters. That's my delta y. Right? And it's going from here to here this way, my delta y. So my work done by gravity is equal to Fg, which is m times g times delta y times cosine of, since my Fg is down and my delta y is down, is 0 degrees. So my work done by gravity is equal to 3 times 9.8 times 0.05 times 1. So work done by gravity should come out to positive 1.47 joules. Then work done by spring. Well, how much work is being done by spring? So work done by spring is equal to, right, work done by spring. You cannot say, F spring dot delta y. Why? Because it is not constant force. We have to use negative 1/2 times k times x2 squared minus x1 squared. We derived this in your notes. I think I told you to memorize that. Okay? So where's my x2? My x2, x final, is here. So this is my x final. And here's my x initial. All right? So if you want to, you can replace the 2 and 1 as final and initial. So you can say work done by spring now is equal to negative 1/2 times k value, which is 90, times x final, which is 0.327 squared, minus x initial is 0.277, oh, I'm running out of room, squared. Sorry. All right, I should write it down here. So here, so work done by spring comes out to negative 45, and then this squared minus that squared. When you multiply them all together, again, negative 1.36 joules of how much work is being done by the spring. Notice it's not exactly the whole thing as the work done by gravity. There has to be, it took some energy away, right? It took some energy away, but not all of it. Okay? So where does that energy go to? Well, it goes to kinetic energy of this object moving. Okay? So that's for part B. So this is part A. So for part B, they ask, what is the speed of the block? Well, for part B, the net work is equal to, right, change in kinetic energy. Well, what's my net work? Net work is basically work done by spring, right, plus work done by gravity. That has to equal to, right, kinetic energy final minus the kinetic energy initial. So work done by spring, we said it was negative 1.36. Work done by gravity was positive 1.47. Right? That is equal to 1/2 mv final squared. That's what we're looking for. We're looking for the final velocity when it reaches the equilibrium position of the block spring system. Here's the initial, V initial, right? When it reaches the maximum height before it drops back down, my initial at this point is 0. And so is here, right? This velocity is 0 here as well. So the highest and the lowest point, the velocity at those 2 points is going to be 0. So here, this goes to 0. So if you work this out, you're going to get 0.11 is equal to, right, 1/2 times 3 times VF squared. So my VF is equal to square root of 0.0733, which comes out to 0.271 meters per second is my VF. So that's the speed of the block going through the midpoint of the oscillation. All right. Any questions so far? All right. What about part C? What is the total work done on the block as it goes from top to the bottom point of its motion? Well, from top to bottom, the oscillation, here, my speed is 0 here, my speed is 0 here. So what is the change in kinetic energy? So from top to bottom, right, of oscillation, the V initial at top is 0, right? Oops. VF at bottom is also equal to 0. Therefore, no net work done, right? Because change in kinetic energy is 0. Therefore, work done by spring is equal to work done by gravity. Because when you add them up, they become 0. So as work is done by gravity, the work done by spring is taking that away, right? And then conversely, as the work is done by spring, the work done by gravity is taking that away. So they're pretty much taking each other away. And we're done. All right.